好，我们继续哈。我刚才上到这一页的时候啊，本来想要讲一下，想讲一个东西，我想我先把 slide service wave slide 冲完再说哈，因为等到冲到完的时候忘记我要讲什么了。同学刚刚上完哈，刚刚这一堂课我们讲 service wave， 上完你一定有一个疑问，就是说，那这个物件是不是用来冲啥？哦，那到底要做什么？它的形式看起来好像还蛮复杂的哦，然后又是虚部又是实部，又搞得很复杂。那我学这个东西干嘛哦？老实讲啦，我第一次学 service wave 的时候，一开始也是被它的那个 representation 搞得头都很胀很痛了哈。光是你要去验证它式子的正确性或那个实部虚部哪边对不对，那些其实就很头大了哈。根本没有那个力气会去想到说这个是要用来干嘛，但我觉得它的 service wave 现象里头比较重要的，直接你可以看到它的应用是这一页了，所以根据这一页的结果，你觉得 service wave 的这个东西要来怎么用？有没有人想到？我不知道你有没有想到哈？它的直接应用是遥测啦 ，remote sensing， 它有点像是我们在做雷达的侦测哈。当然，雷达侦测、雷达应用的话，你是在可能没有目标物的地方找到一个目标物，而这个的话比较像是你知道那个地方有东西，但你不知道是什么东西，然后我们用打电磁波的方式。然后根据它的反射去知道它是什么东西，所以这里头的物理现象告诉你的是什么？当你在 critical region 或者是全反射这个现象产生的时候，其实也不一定是全反射啦。即便是没有全反射的时候，你知道一个重要的现象是 perpendicular polarization wave 跟 parallel polarization wave。它的反射系数是不一样的。当你斜向入射的时候，它的反射系数是不一样的，对不对？所以你事实上是可以用垂直极化跟 perpendicular polarization 跟 parallel polarization 的反射系数的侦测、反射现象的侦测，来去猜测你在看什么东西。所以你假如以遥测的用途的话，你的发射源可能放在飞机上面，或者是放在卫星上面，然后你往下看嘛，那你觉得你要看什么？看地底下有没有石油啊？有的话我们就可以发大财啊，对不对？所以其实好几年前澳洲就有那个就是小飞机小飞机就拖着透地雷达或者是那个所谓的遥测的雷达，在那个澳洲的，我们知道澳洲底下可能有一些油层或者是煤层嘛，所以他们就拖着那个东西飞啊飞啊飞啊飞，那根据侦测的结果，因为它当然不可能是光学频段嘛，光学频段看不进去嘛，但你只要是微波频段，频率低一点，波长大一点，你可以看深一点，所以你是有机会看到地底下用这种遥测的方法，遥测的方法好处在于快啦，你可以在比较快速的时间内扫一大片的范围那以前还要找人开飞机，你现在可以用无人机啦，对不对？所以你可以用那个电磁波打下去，它的那个反射系数不一样的那种方式，那来去理解地底下结构是什么样的多层结构我们今天第3堂课大家也会讲到多层结构的一些反射所以你只要把这一方面的知识合在一起，其实你可以去发展一些应用来去做来去侦测来去做一些那种非接触性、非破坏性的探勘侦测，好不好所以你就所以这种事情也就是说这个现象，也就是因为不同的材质，所以它的反射系数不一样它造成的物理现象叫 depolarization。depolarization 中文要怎么讲？ 罗老师记得吗 ？depolarization。反正就是它那个反射波的那个极化现象跟你的入射波会不一样哦，所以这个 depolarization 的现象就可以拿来去反推或估算说，你看的目标物是什么样的多层结构啊，或者是什么样的特定材质，推估它的那个材质特性啊等等，所以这个东西啊，这种反射现象的物理事实是很有机会来去发展出一些不同的应用啊。那你今天我们刚才讲的例子是，可能你在地面上做探勘，那就是遥测嘛。那它也可以拿来做什么？那照在人身上就变成是非侵入式的医学影像，或者是医学侦测嘛。其实也可以啦，哦，也可以做，也可以往这个方面想啊。虽然凡是扯到医学哈，扯到打人体，就会跟那个什么食药署或什么 FDA 还是啥的扯上关系。对于工程师来讲哦，反正你跟 FDA 扯上关系，对工程师来讲都是非常沮丧的事情啊，因为他们的毛特别多之类的哈，对。Alright, so in the last few in the last few lecture we have discussed the booster angle, critical angle, surface wave, such kind of topics, and the conclusion is the reflected wave or the transmitted wave are dependent of material properties and incident angle. So what can we do to take advantage of this physical phenomenon? We can take advantage of this phenomenon by knowing that the reflection and transmission, transmitted wave property are functional of material composition and your incident angle, so that we can develop techniques to assess or evaluate the material properties of an unknown target. Okay, so therefore, for example, if you mount this kind of sensor on an UAV, you can use to explore the land, explore the Earth, to check if we can find some place with rich mineral concentration like coal or petroleum, something like that. And you can also apply these techniques for medical purposes, okay, because they are the so-called non-invasive measure, 非侵入式的一个方法 using the electromagnetic wave to develop non-invasive diagnosis techniques for medical purposes, right? Now, so the reflection and transmission phenomenon we discuss here has the potential to be developed into different kinds of application. And the next topic we'd like to discuss, propagation in low C medium, is also related to what I have just said. You can use this knowledge to develop some remote sensing or diagnosing tools. Okay, so let's check up with what happens for propagation in low C media. So, of course, we know that if you have a low C media, what is the main cause of loss phenomenon? 电磁波耗损的来源是什么？我常讲的一件事情，就是电磁波怕水。电磁波怕水嘛？为什么会说电磁波怕水？因为水有什么导电性，有导电性。所以材质特性啊 ，among the three material EM material property, the permittivity, permeability, and conductivity. The conductivity is the main source for signal attenuation. the principal source of signal attenuation. Because of the conductivity, you have the so-called, you have this constitution relationship. Sigma, yeah. Because of the presence of conductivity, then if you have an electrical field from the outside, then you will the so-called induced current. And current itself carries energy. So that is, because due to the presence of conductivity, you convert EM field energy into the form of electrical currents. So more or less, the energy is dissipated more or less due to the conduction current, due to the presence of induced current. 所以只要你的材质有导电性，它就会造成真实的电流，通常是 conduction current 但有的时候是 convection current 那种正负离子跑的那种电流，那种真实电流的出现，就会造成能量的耗损。但是反过来有另外一种电流叫做 displacement current 不知道大家还记得吗？位移电流 displacement current。On the other hand, the so-called displacement current, which it appears in the form of current. I mean, the effect of displacement current is current, but itself doesn't involve any charge movement in the medium. 因为 displacement current 你可不可以简单的讲一下什么是 displacement current？我不晓得啦，你只要以后毕业去面试公司的时候，会不会有人问你这些基础电磁学的问题啦？但是我觉得，身为一个工程师，假如你是要做电波相关领域的事情的话，你可能要试着训练自己，把一些基本的物理简单的基本物理现象，能够快速的解释出来，所以 displacement current 是什么？ What is the cause for displacement current? Displacement current is induced by the presence of electrical dipole moment because in atomic or molecule structures you have positive and negative charge. And due to the presence of external electrical field, the electrical dipole moments in molecules or in atomic structures will rotate align with the external E fields. Okay, so if the E field is pointing this way, then positive charge will goes up, negative charge goes down. And if you have an alternating EM wave, then the electrical dipole moment will be rotated as well. Okay, and usually this kind of rotation will not dissipate the electrical power, but for some cases, such as the microwave, in the microwave, the hydrogen molecule, the hydrogen 氢氧键的氢氧食物里头那个氢氧键 the hydrogen molecules hydrogen bond within organic material will rotate, and the rotation will dissipate certain amount of energy. And you use this physical phenomenon to heat up the food. So that's how microwave oven works. Okay, but it carries induction current as well. So providing that you have providing you have the hydrogen molecules. All right, so back to these slides. So let's begin with normal incident, which shall make your life easier for propagation in lossy medium. Here we have two material, medium 1 and medium 2. Alright, we didn't specify which one is lossy, so it seems to me that according to the plot, medium 1 and medium 2 are both lossy because you characterize them with mu1 and epsilon E1 and epsilon mu2 and epsilon E2. Mu1 is permeability, as you know. Epsilon 1 is permittivity. However, here is the permittivity, effective permittivity is epsilon E1. So, which means epsilon E1 is not a pure real number. If you have a lossless medium, then epsilon 1 is a is real. Now, for lossless material, epsilon 1 is a pure real number. And for lossy material, epsilon 1 or epsilon E1 is a complex number. Is a complex number. Then the imaginary part of epsilon E1 shall represent the cause of the lossy component. So we know that for propagation in lossy medium, the propagation constant is a complex number comprising alpha and beta, alpha plus j beta. Beta is the phase change, where alpha is the attenuation constant. So the cause for non-zero alpha is this thing is not purely real. Okay, if this thing is a complex number, you end up with a gamma 1 as a complex number. Okay, then the real part represents the attenuation. So not only the propagation constant is a complex number, the intrinsic impedance of the material 1, eta 1, should be a complex number as well, because epsilon E1 is a complex number. Okay? Now, if epsilon E1 is a real number, then you have a real eta 1. Here you have a complex eta 1. So what is the implication of this result? eta 1假如是一个复数的话，有什么样的结果？ eta 1是纯实数，代表什么事情？老师在上那个大学部的电磁学的时候，一直强调eta本质阻抗是什么东西？它的单位是欧姆，但是它不是电阻啊，对不对？ eta 虽然单位是欧姆，但是它代表的物理意义是什么？材料里头的电场跟磁场的比值嘛，对不对？材料里头的电场跟磁场的比值，空气是377，所以电场大小是磁场大小的377倍。你在水里头呢，会是磁场比电场大；你在空气里头是电场比磁场大。好了，那假如你的 epsilon E1 是一个 complex number 的话，你的 eta 1也是一个 complex number。那一个 complex 的 eta 1，它的物理意义是什么？ complex eta 1，它的 magnitude 代表的是电场跟磁场的比值，还是一样。但是因为它是一个 complex number， 所以它有相位，它表示是什么？电场跟磁场不同步，它们之间有相位差，它们的相位差就是 eta 1的相位，可以吗？哦，你的 eta 1就是你电场除以磁场嘛，E除上 H 嘛，所以 E除上 H 只要不是一个 real number。 假如它是 real number， 那就表示它们的 phase 同相位。那假如是 complex number， 就是它们的相位不同嘛。所以电场可能会领先磁场几度，或电场落后磁场几度。假如你还记得我们在讨论那个导体的那个 propagation constant 的时候，你会发现那个时候我们导体的结论是什么？ 只要是一个导电材料的话，它的结论是阿尔法等于贝，阿尔法的大小会等于阿尔法等于贝塔，所以一个阿尔法等于贝塔的阿尔法加 j 贝塔会等于什么？阿尔法的1加 j 嘛，所以表示什么？在导体内部，它的 propagation constant 是45度，哦，电场领先磁场45度 ，OK， 对于导体的话，你就有这样的结果。 All right. So you need to be aware the implication of having a complex eta 1, complex intrinsic in principle. The complex intrinsic in principle indicates that there is a phase difference between E and H field for this propagating wave in this medium. So accordingly, we can write up the reflected wave. As we already know, the reflected wave can be returned as the incident wave times the reflection coefficient and the boundary. So here you have gamma B for your reflected E field. Here you have a reflected H field. Note that there is additional minus sign over here, representing the change of propagating direction. Originally, because the reflection, the incidence and the incident wave and the reflected wave have opposite propagation direction. So the minus sign here is required to change the propagating direction of the reflected wave. Okay, and here is the in this plot you can see that this is the incident wave, this is the propagating direction, this is a TEM wave, of course. So this is the E field direction. Okay, and then here is the reflected wave, here is the transmitted wave. And we can also do the same thing for the transmitted wave. So note that here is the transmission coefficient. You replace the transmission coefficient to adjust the magnitude and phase of the transmitted wave. And the propagation constant should be replaced with property within median 2. Okay, so as you can see here, gamma 2 is in the z direction, and its content is alpha 2 plus j beta 2. This is only valid for normal incidence. Okay, in the previous slide we already specified that this is a normal incidence. So the transmitted wave is also propagating in the z direction. So the propagation constant of the transmitted wave is simply using the alpha gamma 2 times z times z-axis in the z-axis, and the magnitude of this well, the alpha 2 plus j beta 2 can be found by using the frequency and material property mu and epsilon. All right. And here is the reflection coefficient and the transmission coefficient, and this thing's only valid for normal incidence. Okay, if this is not normal incidence, if it is, if the incidence has an oblique incident angle, then you will have different representation for perpendicular polarization and parallel polarization. Okay, but when it comes to normal incidence, there's no difference in perpendicular polarization and parallel polarization. So they are supposed to have the same. They are supposed to have the same reflection coefficient and transmission coefficient for normal incidence. Again, if median 2 is lossy, then eta 2 should be a complex number. And the reflection coefficient, transmission coefficient are supposed to complex number as well. So let me ask you again, what is the implication of reflection and transmission coefficient as complex number? The implication is with complex reflection and transmission coefficient, the reflected wave and the transmitted wave, the E and H field in the reflected wave, the phase difference between E and H field shall be changed once it times the reflection coefficient and transmission coefficient. So the reflecting and transmitting behavior will change the phase difference between E and H field due to the presence of complex reflection and transmission coefficient. And furthermore, because this is lossy medium, so if you calculate the average density. That is the Poynting vector. That is the product of E and H field. You have S, the Poynting vector, the power density, and here is the time average result. So you kind of taking the, as we have seen earlier in the incidence. That means is the it's the real part of the. This is time average. This is instantaneous. So you take in the real part of your instantaneous Poynting vector. You end up with time average Poynting vector. So because you are taking the real part, so here the exponential is reduced to only the attenuation part. So you have here, you have exponential minus 2 alpha 1z, which means as you further proceed, further propagate in the z direction, the magnitude of the Poynting vector reduces with this relationship. And the very last term, that is the real part of 1 over eta 1 conjugate, simply is the magnitude of, no, not simply, not just the magnitude, just the real part of eta 1, okay, real part of the eta 1. Well, it's just an adjustment in the Poynting vector magnitude, okay? So using the same method, you can write up the reflected average power density. So the difference is with the incident part is here. Not that the change of the minus sign over here. This is positive because now you are propagating toward the minus z direction, right? And here is the transmitted part. So on top, so you also have the square of transmission of the magnitude of transmission equation, transmission coefficient. Here you have the square of the magnitude of transmission coefficient, reflection coefficient, transmission coefficient. Okay, positive z direction, negative z direction. Material is eta 2 over here, eta 1 in the original for the reflection. 所以电磁学就是要细心啦，你就是式子他们不是式子都要写3遍所以你要去然后 check 一下那个式子上面各个式子之间不一样的地方，好不好？好，所以对于 normal incidence， 其实你就是考虑一下那个材质所造成的差异，有没有注意到？刚刚我们前2页讨论的是 normal incidence。normal incidence 其实这个状况不算太复杂，你只是要把 eta 1、eta 2的材质差异考虑进去，所以它会影响到反射系数，会影响到相位的那个变动的那个相位变动常数，影响到传播常数。但接下来我们要看的事情是 oblique incidence。Okay, so next thing we will look into the case for oblique incidence. And that should be very interesting. The situation will become much more complicated than the normal incident case. So let's move on. We already know that for lossy medium, the effective permittivity becomes a complex number. But in fact, the reason why epsilon E2 is a complex number is because of the presence of the conductivity. 所以我们说耗损的万恶来源之首就是导电性。So you can actually rewritten the epsilon E2 as epsilon 2 as a pure real number with imaginary part of sigma E2 over omega. And the sigma E2 is what? The effective conductivity within medium 2，材料2的那个导电系数 And you know that, so you know that the attenuation is related to conductivity and frequency as well. Here you see the dependence of sigma and the dependence of omega. Therefore, so because of the presence of conductivity in the material, it will cause loss of the propagating signal. And here we have the case of medium 1 is a lossless medium. So epsilon E1 is a pure real number. Epsilon 1 is a pure real number. On the right hand side, the medium 2 is a lossy medium. So epsilon E2 is a complex number. We shall keep mu2 as a real number, so for simplicity, without loss in generosity. So let's just have epsilon E2 as a complex number as specified here. Okay? And here are the representation for incidence, reflection, and transmission. And we know that beta I is the phase constant vector for the incidence. So according to the incident angle theta I, beta I can be written like this. It's a dependent of medium 1 material property, and the second part is the incident angle. Here is the phase propagation constant of the transmission, which can be separated into real part alpha 2 and imaginary part beta 2. And because of the presence of effective conductivity, alpha 2 is non-zero, so you have loss in medium 2. The propagation constant of the transmitted wave can also be rewritten like this, as the product of the phase constant and transmission angle, transmitted wave angle. Okay. The relationship between alpha 2 and beta 2 and gamma 2 can be specified like this, as we already know. And if you do the dot product of the transmission coefficient, propagation constant of the transmission itself end up with the square of the magnitude of the transmission of the phase propagation constant in medium 2. Okay. So let's move on. Here's the Snell's law of refraction. Snell 的折射定律. Okay. And it's still valid for complex propagation constant. So in the red box is the Snell's law for lossless medium. If both sides are lossless medium, you have simply the beta 1 times sine theta I equals to beta 2 times sine theta t. If they are replaced with lossy material, the Snell's law of refraction still holds. So you have J beta 1 sine theta I because material 1 is lossless. Material 2 is lossy, so you have alpha 2 plus J beta 2 times sine theta t. So using the Snell's law of refraction, you can rewritten sine theta t as material property on the two sides and angle of the incidence. Okay, so here you have sine theta t, which is obviously a complex number. Well, this part is complex. Even though this part is real number, this part is complex number. So sine theta t ends up as a complex number. cosine theta t should be a complex number as well. So according to this result, sin theta t is complex number, cosine theta t is complex number. So if you goes back to here, then this thing, the propagation, the propagation constant vector of the transmitted wave is a complex number times this vector, where sin theta t is a complex number, cosine theta t is a complex number too. So these things can be very scary, all right? 整个全部都是那个 sin theta t 也是负数 ，cosine theta t 也是负数，前面那个 alpha 2加 j beta 2也是负数啊。So we go back here, then, we know that it's a complex number anyway. So we write up cosine theta t as magnitude s times exponential j zeta, OK? 那个希腊字到后面有几个字都长得差不多长长的但是那个抖动不太一样所以有兴趣的可以 Google 一下看一下他们怎么念的像这个念 zeta 对 zeta OK So the complex number part exponential j zeta can be rewritten as cosine zeta plus j sin zeta. Okay. So you use the polar coordinate system to represent this complex number. Alright, so cosine theta t is a complex number, sin theta t is a complex number, everything is complex number in the representation for gamma t. So what matters? What matters is we should learn the influence. We should learn the influence of gamma t as a combination of complex numbers. Okay, so we replace cosine theta t with s times cosine zeta plus j sin zeta. Sin theta t is a little bit simpler. We can substitute it with Snell's law of refraction. So sin theta t is replaced with beta 1 sin theta I times j divided by alpha 2 plus j beta 2. And in the front is the propagation constant of median 2. So it's simply as alpha 2 plus j beta 2. And we try to simplify the representation a little bit. So as you can see, the alpha 2 plus j beta 2 part can be cancelled for the first component. Well, in fact, for the x component. For the x direction component, you have a relatively simple representation that is j beta 1 sin theta I, which is purely determined by your incidence, theta I, incident angle theta I, and median 1 property, right? So the x direction part is relatively simple. The z component is not that simple. The z component, you have alpha 2 plus j beta 2 times s times cosine zeta plus j sin zeta, okay? And zeta is another complicated things. But anyway, let's try to sort it out, all right? 我们试着把这个东西乘一乘这里头你看到，因为是两个 complex number 相乘嘛，对不对？所以它其实会变成四项。那四项有2个是实数，2个是虚数。事实上有2个是实数，2个是虚数吧？OK 所以我们用实数跟虚数来去区分了因为 alpha、beta 本身cosine zeta、sin zeta 本身是实数了所以 所以后面那个 z 后面跟着它是两相乘嘛，它有4项嘛，所以我们把它里头的那个实部提出来。所以实部 the real part of the z component contains alpha 2 as cosine zeta and minus beta 2 as sine zeta. Okay, so they belongs to the real part. The imaginary part has the product of this with this one with this one. So you have 2 s cosine zeta plus alpha 2 s sine zeta, along with the x component. Along with the x component. 当然，你回家要推看过一次，自己跟自己确认，讲义或者课本上写的没有错。但重点还是结果的 interpretation 啊，结果指的是什么事情啊？所以，当然因为上课的 lecture 的时间有限，老师也只能讲的就是说它的结果真正代表是什么意思啊？好，所以推到这边的时候，你发现你有，当然上面的式子你是根据 in this line you have x component and z component. In this line you divided them into real component and the imaginary component. So let's check up with the real component and imaginary component. For the real component, can be substituted with alpha. As you can see here, the real components lies in the z direction only. Alpha 2 is along the z direction only, and the content is s alpha 2 cosine zeta minus beta 2 sine zeta, whatever it is. Okay. Okay. Let me notify you the confusing part, okay? 这里有比较讨厌的事情啊，是alpha 2 and beta 2 are dependents of material description. Similar to what we have discussed in surface wave. The vector representation of alpha 2 and beta 2 are combination of material property and incident angle. Okay? So that's the reason why you have this thing. 只要你没有从刚刚前面一路推导下来的话，直接看到这个会觉得靠，这是什么东西啊？OK。所以 alpha 2 and beta 2 as a scalar number is purely determined by the material property. However, we are talking about the transmitted wave property. So for the transmitted wave, the real power of the propagation constant alpha 2 and the imaginary power of the propagation constant beta 2 are not only determined by the material property, is are dependent of the material property and the incident angle. Okay? So here is the material property. This involves the incident angle. So check the two. What can you tell from the two relationship? Alpha 2 is aligned with the z-axis only. On the other hand, beta 2 means what? A propagating wave. The propagating wave has S component and Z component at the same time. As long as you have oblique incidence. If this is normal incidence, if this is sin I is 0. So you don't have X component for your transmitted wave, propagating transmitted wave. But if you have an oblique incidence, sin theta I is non-zero, then the beta 2 vector is pointing toward something somewhere different from normal direction. So the interesting we have here is alpha 2 vector and beta 2 vector are neither parallel nor perpendicular to each other. Alpha 2 is pointing along the normal direction of the interface, while beta 2 is pointing somewhere else from the normal direction. Beta 2 is a dependent of theta I, the incident angle. 好，所以这边要注意它的差异So okay, so we have a graphical representation like this. Alpha 2 is pointing to this way. So the wave magnitude attenuation direction is in fact different from the phase change direction. So beta 2 is the phase change direction. Alpha 2 is the attenuation direction. So 所以你看起来，假如在 lossy medium 里头传的波它的那个相位跟大小的变化就看起来很复杂了。不要讲很复杂，很有趣了Very interesting. Okay. So alpha 2 vector represents the direction of attenuation. Beta 2 vector represents the direction of phase variation. They are different direction for lossy medium. They are the same direction for lossless medium, but they become two different directions for lossy medium. So what is the parameter that describes the difference in beta 2 and alpha 2? Is this phi 2. The angle phi 2 is used to specify the difference between alpha 2 and beta 2. We know that the dot product of two vectors can be represented as the product of the magnitude of the two vectors times cosine phi 2. Where phi 2 is the angle between the two vectors. Okay? Now you can directly get the very beginning, the end product of the two. If you substitute representation of alpha 2 vector and beta 2 vector in the previous slide, you can end up with that relationship. With some algebraic manipulation, you can expand the product into 4 terms. Okay, 4 terms. You can do 4 terms, and you can try to collect them in. You can try to we can sort out the things a little bit, but I don't see any implication. 看起来没有简化到什么程度吧OK， 它还跟 zeta 有关zeta 的话在前面几页还有点复杂好。But anyway 你可以找出那个 phi 2的角度根据假设上面这些东西都已知的话，那个 phi 2角度还是可以知道的你会知道那个 phi 2角度也是跟你的那个材质的参数跟你的那个入射角 theta I 有关系的Okay. So here's another way to okay. So here's the here's another way to look into the representation of or the difference between alpha 2 and beta 2 vectors. Okay. So here we have alpha 2e times So here we kind of separate the phase function. Okay, so this is the phase function of the transmitted wave. We try to separate it into three terms. The first term is the attenuation along the z direction. The second term is phase variation along the x direction. So let's say this part as mu, that is beta 1 times sine theta I. And the third part is the phase variation along the z direction. So let's substitute it as q. Then the phi 2 direction will be the angle between mu and q, which can be simply found as the arctangent of mu over q, right? So this is its projection along the x direction. This is its projection along the z direction. So the angle phi 2 is arctangent of mu over q. And beta 2e, the overall magnitude is mu to the square root of mu to the square plus q to the square, right? 好吧，所以我们这边找出 phi 2的那个写法啊 ，phi 2的写法。So the dashed line here again, the vertical dashed line represents the constant amplitude planes. So the amplitude becomes smaller and smaller as u goes further to the right. The slanted dashed line is the constant phase plane. So it's perpendicular to the beta 2e direction. That is the phase change direction in median 2. Okay. So finally, let's summarize. Let's have a summary of reflection and transmission. So we're taking everything into consideration. In this chapter, we learned that the E field can be separated into 这些方框都是那个 parallel 了我不晓得为什么那个 parallel 那个 mark 在 PPT 里头你要装那个程式才看得到了所以这些小空格的那个小框框都是 parallel 也就是 parallel polarization 的那个成分。So we know that the incidence can be divided into parallel polarization part and perpendicular polarization part. And the phase constant vector beta I can be represented with the propagation direction, parallel propagation direction, the cross product of the incidence with the perpendicular polarization, unit vector. This is the unit vector of perpendicular polarization, right? So this is the incidence, reflection, and the transmission. Okay. And here's after the decomposition of parallel polarization part and the perpendicular polarization part, the incident E field can be written like this. And this is the magnetic field representation. I would like to point out one thing. It's written as this. Can you tell the difference? This represents an incidence of arbitrary polarization. 任意的 任意极化的入射波。那虽然说是任意极化，但是它可以被拆成 parallel polarization part 跟 perpendicular polarization part， 对不对？好，所以这个是一个 arbitrary polarization。但是注意到的是当你在拆解成 perpendicular polarization 跟 parallel polarization 的时候 ，perpendicular polarization 的方向只有一个，而且跟你的入射角度无关，所以它才会写成这个样子，就 E hat perpendicular， 也就是例如我们在前面看到的图片里头，你那个拆解的 plane， 你那个 incident plane 是在 XZ plane 嘛，对不对？然后 perpendicular E field 的 polarization 的方向是哪里 ？Y 方向。所以不管你入射角怎么改变 ，perpendicular 都在 Y 方向。So invariant to the incident angle. The perpendicular polarization with the unit vector for perpendicular polarization is always pointing to the y-axis. As we see in the previous slides, invariant toward the incident direction. On the other hand, if you want to describe the incident wave, the parallel component of the incident wave, you need to specify the incident angle. You need to specify the incident angle. This vector, this unit vector is actually a dependent of your incident angle. So that's the reason why in the textbook, the two are right a little bit different, okay? I forgot this. So the hat means it is a unit vector. But you need to specify I over here because it's the parallel component is a dependent of the incident angle, while the perpendicular component is always pointing toward the y direction and is invariant toward the incident angle. So we say E hat perp is the same in all cases. Okay? Now that's the one thing I need you to be aware of. So here's the reflection. So again, parallel component and perpendicular component is a little bit different. Parallel component is the unit vector for parallel component is a dependent, is a function of incident angle, and so is the transmission part. Okay. All right. So here's the very last page of the above discussion about reflection and transmission in two media. The polarization characteristic of reflection and transmission, how to determine them. First, we determine the polarization of the incident field. Then we write the field in terms of parallel component, the unit vector of the parallel component and the unit vector of the perpendicular component. As I mentioned earlier, the perpendicular component direction is the same for all cases, while the parallel component direction, the unit vector for parallel component is a function of the incident angle. And then we can find out the reflected wave and transmitted wave, right up there. Field representation in terms of unit vector for the reflected wave in parallel direction and perpendicular direction, as well as for the unit vector for the transmitted wave in terms of parallel direction and perpendicular unit vector in parallel direction and perpendicular direction. Then we can determine the polarization of the reflection and reflected wave and transmitted wave. Again, due to the difference in reflection coefficient and transmission coefficient, we can use this property to I mean the difference in reflected wave and transmitted wave for oblique incidence. We can use the oblique incidence. We can use oblique incidence to probe or to investigate the material property of your unknown target. 因为你看到的事情就是说，电磁波的极化特性会跟你遇到的材质，然后会跟你入射的角度有关。那入射角度你可以调很多方向，所以意思就是说，你看的方向越多，你对于根据那个结果，你对于那个材质，你对于目标物的材质特性就可以分析的越透彻。举个例子来说 ，MRI 知道吧？那个核磁共振影像或者核磁造影啊，在医学工程里头，你事实上用微波或者是一些更高频率的电磁波，为什么要更高频率？更高频率它吃进去那个人体里头更深了高能粒子吃进去更深。所以在 MRI 里头，你一些比较厉害的那些医学影像，你都要做，你要做一个2D 的扫描嘛，对不对？你去看牙医的时候，现在应该比较牛逼的牙医诊所都有那种3D 照你的那个口腔的那个牙齿的 X 光片嘛，整个这样绕过去，所以它是用空间换取，它是用不同的角度 angular domain 的 different angular domain 的那个 diversity 来去换 spatial domain 的 resolution。你今天只要只是一个方向看过去，那就是有没有你有没有遇到那个骨头的障碍物？但是你只要绕一圈下来的话，你加上各个方向的那个的 information， 你就可以把它遇到障碍物1维的遇到障碍物的这些事情，在2维的空间里头组合起来，那你可以得到3维的成像所以你可以看到一个类似立体的那个口腔内部的那些骨头的位置的分布了看是牙齿的骨头还是钢钉啊什么这些的OK。我看我们还是先休息一下好了，然后接下来再讲下一个 topic。夕阳休息5分钟。